Okay, good morning.
Good morning.
This is chapter 8, okay? Elasticity using finite element. Essentially, we will just rewrite the formulas that we derived last two lectures, which is in tensor notation form into matrix form. The reason we want to write it into matrix form is that it will reveal more clearly the physical relationship between various quantities and also easier to program. Okay? So the purpose of this lecture is to express the weak statement of elasticity in 3D, and also it includes 2D in matrix form. Okay, so let's just review briefly the weak statement that we went through last lecture. Is integration of sigma ij and then delta epsilon ij dv. So this is integration over the whole elasticity, the solid body. Okay, this is the v, and the boundary part of it is essential boundary condition. We call this part of the boundary as U. The other part is as T. This is traction boundary condition. Okay. All right. This is equal to integration of body force with delta Ui dV. Then plus this is integration over the body. And then plus a surface integration term. This surface is over traction boundary only, Ti, delta Ui, and then dx. We went through the details of the derivation. First, I'd like to draw your attention to the expression here. On the left-hand side, what kind of indexes do we have? Free or dummy? All dummy. I appears twice, so that's dummy. J also dummy, which means summation. So you should understand that with a summation in front that says sum with respect to I from 1 to 3. And then there's also J, another summation sign, sum with respect to J from 1 to 3. Okay, you need to understand that because that is implied in this course. And here, this term, we also have another index, I and I here, and because it appears twice, that's also a dummy. Therefore, in front, you should kind of imagine there is a summation sign, I is from 1 to 3, okay? And here is the same. Physically, when you have a stress times a virtual strain, stress times strain give you the strain energy density in terms of physical dimensions. You integrate over the body, it means all the strain energy stored in that body. Imagine any solid as a spring, okay? So this is the spring energy or the elastic energy stored in the body. This is body force times a virtual displacement. Force times displacement give you the work done by the force, right? And again, body force is distributed over the whole body. Therefore, when you integrate over the whole body, that means all the forces on the body done on the virtual displacement. So this is work by the body force. Now, very similarly, you have a traction, which is a surface force times the virtual displacement. So this is the work done by the traction boundary condition over traction surface. And again, this is work done by surface traction. This is work done by body force. So on the right-hand side is the work, the virtual work done by body force and traction. The right-hand side is the elastic strain energy stored in the body. So it has a very clear physical meaning. It's just the same as the principle of work and energy. Okay? The work done is stored in the energy form, elastic, because we assume there's no temperature change, there's no other form of energy dissipation, no plastic deformation. That is why the force done is stored as a spring energy. When there is plastic deformation, that's a different story. And if there is plastic deformation, the energy will be changed into heat, then the temperature will change. You no longer have these kind of work and energy principles. It will have a different form. But we know that if you have a spring, purely elastic, however you work it, it will never change the temperature. Because the deformation is elastic. So this is a very important point to remember. All right. So this is the weak statement of elasticity, but right now is in index form. And also, let me ask you, how many equations these represent? Is 1 or 6 or 9 or 3?
Just one.
Just 1, correct. Why is 1?
Just every
Because
so.
this is summed together. There is no free index. When there is a free index in 3D, it usually means 3 equations. Because that free index I can take on the value of 1 or 2 or 3. So it represents 3 equations, or 2 in 2D case, okay? But when all indexes are dummies, you sum over, so it's just 1 equation. All right, next we're going to change that into matrix form. So now let's write, we use vector, column vector, row vector, okay? So we are going to write sigma vector, instead of using 9 component, we know a stress has 9 component because it's symmetric, only 6 are independent. So we are going to write only the independent component, sigma 1,1, sigma 2,2, sigma 3,3, and then tau, or let's keep using sigma 1,2, sigma 2,3, sigma 3,1. Okay? And then the virtual strain vector, again, we're going to write it as a column vector. We have delta epsilon 1,1, delta epsilon 2,2, delta epsilon 3,3, and then delta gamma 1,2, delta gamma 2,3, and then delta gamma 3,1. Okay? I'd like to draw your attention here. When we write the stress in a column vector, these shear components are just 1, 2, 2, 3, and 3, 1. When we write the strain component in a column form, we use engineering shear strength here, not the epsilon 1,1, epsilon 1,2, or epsilon 2,3, and epsilon 3,1. And there's a reason, okay? However, we know the strain shear, the tensor shear strain and the engineering shear strain, the relationship is a factor of 2, right? So this is equal to delta 1,1, delta 2,2, delta epsilon 3,3, and delta 2 delta epsilon 1,2, 2 delta epsilon 2,3, and then 2 delta epsilon 3,1. Okay, so pay attention to the coefficient factor 2 in front. Here, here, here. Okay? Why do we do that? Why there is a factor of 1 here, but there is a factor of 2 here? That's because if you look at this expression, when you write it out, it's equal to this. Delta, sigma ij, delta epsilon ij, when you write out in full, it will be like this. Sigma 1, 1, 2, 2, 3, 3, and sigma 1, 2, 2, 3, 3, 1, and you also have 2, 1, 3, 2, 1, 3. You really have 9 components. Then it's going to times a column vector which also has 9 components, which is epsilon 1, 1, okay, delta, and delta epsilon 2, 2, delta epsilon 3, 3, delta epsilon 1, 2, 2, 3, 3, 1, delta epsilon 2, 1, delta epsilon 2, 3, 2, delta epsilon 1, 3. Because when each of these index run its course, you will have 9 things here. Correspondingly, another 9 things. You times that together, add them, and you can express it like that. At the end, the summation will have 9 terms added together. Okay? But when we want to write it this way, as you can see, this times that. There is also this times that. And these 2 terms are the same. So you can combine them, you have a factor of 2 in front. Okay? So at the end, you can also simply write it as sigma 1, 1, 2, 2, 3, 3, sigma 1, 2, 2, 3, 3, 1. So this is now 6 things. I also want to write it as 6 things. So 1, 1, 2, 2, 3, 3. This time, you have a factor of 2 in front. So 2 delta epsilon 1, 2, 2 delta epsilon 2, 3, and then 2 delta epsilon 3, 1. Okay? So that's where this factor 2 is from. And it also corresponds very nicely to the engineering shear strength. Because physically, that's how it should be. The shear strength energy is shear stress times engineering shear strength. Okay. All right. So the reason the factor is 2, there are a factor of 2 here, is because we shorten a 9 component vector into a 6 component vector, making use of symmetry. Therefore, now this time, once we write it this way, now we can write it as a sigma vector, which is here, transpose. Because we use column vector here, we need to write it as a row vector to finish the multiplication. Therefore now, with this expression, this thing can be written very nicely as that. Okay? If there's no factor of 2 here, then the result will be incorrect. All right. Now we can also write in a very similar way the virtual displacement vector. That's simple, only 3 components. So that's delta U1, delta U2, delta U3. So that's how we represent that. And the traction is also a 3-component vector. So it's equal to T1, T2, and then T3. Okay? All right. Now with all these notation, let me circle it here. This, and this, and that. We can now rewrite this equation in matrix form. Okay? let's do that. So let me erase this. So we can say in matrix form, it becomes, this is a single number. So when you write two vectors times together, you need to be very careful. The front one should be a row vector. The back one should be a column vector. So at the end you have a number. So now we have sigma vector, because it should be a row vector. So we need to write it as a column vector transpose. Okay? And this one is delta epsilon. Now integrate over dv. That's equal to the body force. Again, we need to write it as a row vector. So it's, we can write the body force as a row vector in front, or this as a row vector. It turns out it's more convenient for later derivation that we write that as a row vector. This is a column vector. So we just put delta U in front. In fact, we should do it from the first term. So instead of writing this as a row, this as a column, I would like to write this as a row, this is a column. So I will switch to position. It's delta epsilon in front. Put a transpose there, that's a row vector. And then sigma, that is a column vector. And then here I have a delta U row vector times the B column vector. Integrate over volume plus, and here similarly traction times displacement. I will put displacement in front, so I have delta U transpose, which is a row vector times surface traction T, and then integrate over traction boundary, okay? This is the matrix form of the weak statement that we derived in the last two lectures. Okay? These two are completely equivalent. The only thing you need to remember is that when we write the string as a vector form using 6 components, the shear strength should be engineering shear strength, not the vectorial shear strength. Okay? Okay, very good. I should say the tensorial shear strength, not the vectorial. Okay, it should not be the tensorial shear strength. It should be engineering shear strength. Okay, now next step. This is still in continuum form. It applies to the original body. What we will do next is now to discretize that into element. Okay, like that. With elements, now we assume an approximate solution. Element formulation. What we first do is assume that the displacement field can be written as the shape function times the nodal displacement. Okay? And we use this as the weighting function. Here, this n is the shape function. And in component form, the ith displacement will be equal to the sum of the shape function times delta A I, okay? I should write it as with respect to J here, and with respect to the J, okay, I know what's going on. Because during derivation we use delta U means the x displacement. Now with index, U can be U1 or U2 and U3. So here I should really correspondingly put I here. When I is 1 is U, when I is 2 is V, and I is 3 is W. So the 3 displacement. But this is at the nodal value, okay? This is the nodal displacement vector. So the shape function is going to act over that. And then this whole thing over each node, like that. Well, the shape function is like this. When we are talking about node 1, the value of the shape function at 1 is equal to 1. That corresponds to this 1, the first nodal displacement, okay? And in a matrix form, it should really be like this, okay? This is just an aside. Now, when we write it as delta U, delta V, delta W, so the 3 nodal displacement. This formula is really like this. We have N1 here, and then 0, 0, 0, N1, and then 0, 0, 0, N1. Let's look at that as a submatrix. And then N2, 0, 0, 0, N2, 0, 0, 0, N2, and a submatrix. And then again, it could be very long. It depends on how many nodes your total element model, finite element model has. You can have 100 nodes, 1,000 nodes, like that. So this thing is really pretty long. Here you have delta U1, delta U V1, delta W1. All these 3 components correspond to the first node. And then you have delta U2, delta V2, delta W2 that correspond to the second node up to N. Therefore, this is a 3 by 3 N matrix. N is the total number of nodes of your finite element model. Okay. This one will have a 3n by 1. That's the dimension, where n is equal to the total number of nodes of your model. As you can see, for a 100 node model, this is very long. It will be 300. For a million nodes, it will be 3 million. So it's very, very long. This is again very, very tall. Okay? But doesn't matter. When we write it as a matrix form, it's so simple. It's just here. Okay? So it's very, very important when you write something, you understand what it represents. Okay, because the transpose of U is used, So we can transpose that. Therefore, delta U transpose, and again apply the linear algebra formula. When you transpose something, each of these will be transposed, and also the position should flip. Okay, so you have delta UA transpose, and this shape function matrix here is also transposed. Okay, like that. And then, yeah, I need to erase that, make use of space. Now, remember the formula to calculate the strain. Strains are a combination of the derivatives of this corresponding displacement field, right? We use that we use the B matrix to represent that, and then we have this delta UA. Okay? The B matrix involves the derivative of those things with respect to the corresponding xi. Okay, we derived that last time. Therefore, the transpose of the strain vector, because we need it here, again, these will be transposed. Delta UA, and then transpose, and the B matrix is also transposed. Okay. Now, with this and this into this, we will get this one is this. Therefore, now we have delta epsilon. Delta epsilon is this one. So it is delta UA transpose and B matrix transpose, and then times these sigma here. This is the first term, then equals this term. This delta U transpose is this one. Therefore, now we have delta U vector at the node position transpose times this B body force that is integrated with respect to volume over the whole domain, then plus this term, where this is equal to that, so it's delta UA integrated. Oops. That should be curly bracket transpose times N matrix transpose. And then we still have this traction vector. So this is T here, then integrate over traction boundary condition. Okay?
In the notes, the second term has an N transpose between the delta U sub A and the body force vector.
In the note, which one?
There should be one, yeah.
Which equation? 8-9?
Yeah, 8-9. Your
Mhm.
second term you have on the board there. The notes have a N transpose matrix in between the delta U sub A and the body force vector.
Oh,
Yeah.
let me see here. Yeah, I forgot that
Delta
thing.
U should be.
Because when I substitute this, I only write that one. So I missed a N matrix here. N transpose, actually. Yeah, thank you for pointing that out. And then body force and then dV. Okay? By the way, in the note, I sometimes don't have those curly bracket and square bracket, but because I use the boldface, it represents matrix or vector, depending on the situation. But when in handwriting, it's just impossible or very difficult to write a proper boldface letter. So we use these to denote This is a vector, that is a matrix, okay? That's a quick note here. All right, what we are going to do next, okay, now because we obtained that equation, we can erase this here. Up to this point, now it is in matrix form. How many equations does this represent? Can you recognize?
Should still be 1,
Still be 1. Why?
because it's the same problem.
Okay, you can just look at, well, they all have root terms. This is a row vector times a matrix. At the end, it's a column vector. The the intermediate ones, the dimensions always disappear when you have one thing times another times another. What determines the row, number of rows is always the first thing. What determines number of columns is always the last thing. So you have one row and one column, and then you have a single number. So if this is a single number for consistency, all these should also be single number. So this is one equation, okay? So you need to recognize that. And then what we are going to do next is to magically transform these into a system of equations. How? Well, we can just rearrange and combine. In fact, we can move everything to the left-hand side, and this is a common factor, and take it out. So you will have a common factor times a bunch of things equal to together. And then we argue that because that factor is arbitrary, what is inside should be 0. So that's what we're going to do. So let's rearrange. We have delta, because what is in the curly bracket is the nodal displacement vector, which is not a function of the position, the coordinate x, y, z. Okay, so this is as far as integration is concerned, because the integration is with respect to x, y, z. So they are constant. You can take that out. Okay, all this here, and they're also common. So let's take that out. So this whole thing now times an integration over the volume. The integrand will be what is left here, B matrix transpose, oops, write it properly, and then sigma dV. And then we have this moving to the left, we have negative sign in front. So we have N transpose B dV B minus, and then N transpose T dV, this is ds over st. This whole thing equals 0. Okay. All right. Now we write a vector, a row vector times that. That must be a column vector. Okay? Equals 0, still one equation. The next, and then next, we're going to make the argument that because this equation should hold for any nodal displacement. When you apply the load a little bit, this is small, right? When you apply it larger, it will be large. So it doesn't matter. It should hold all the time. Then we argue that because this is arbitrary, then these things should be equal to 0 all the time. Okay? Since delta UA is arbitrary, we have what is inside must be 0, must hold true in order for this thing to hold true. Okay? So now, you get that, this is sigma dV integrate over B minus n t B vector dV minus n transpose T ds integrate over st. That should be 0. Okay? Now let's see how many equations these one represent. M,
And
n. What is n?
the number of nodes,
Number of nodes.
or number of elements. One of them.
Number of nodes. It should be nodes. In 1D is n. For 3D problems,
3 and 5.
actually
3 and 5.
in 3D, it represents 3n equations. Because when you look at this one, okay, okay, the n here, remember, is 3. The n, the shape function matrix, when I write it here, is 3 by 3n. Now transpose becomes 3n by 3. Therefore, for this transpose, the number of rows is 3n. That is why you have 3n equations. Okay? Because, as I mentioned, it's always the number of rows in front that determine the total number of rows. If this is 3n, it means 3n equation. Okay, by making this argument, we change a 1 equation into 3n equations. Now we have a system for equations to solve. And this is a pretty important result. It is not the final finite element system equations that we are going to program. However, I would like to mention that a lot of explicit code is using that. Okay? The reason is using that is when you do an explicit calculation, you don't solve equations. You iterate. You just assume in the current state you know everything. You start with a no condition, right? A no state. And you ask next small step in split second, like 200 milliseconds, what will happen? Then you use this equation to predict what happened next. You don't actually solve the equation. You just use that as an approximate way to predict things. Okay? And then you get the next state and you march forward. And it turns out this is very convenient for explicit code. Okay? This is used in explicit FEM a lot. For static problem, for dynamic problem, okay, explicit code are usually for dynamic problem. However, in this course, we focus on static problem. And the code we call it, or the method, the FEM method, is called implicit code. Okay? This, for the explicit code, for example, LS Dyna is a well-known explicit code for dynamic problem, for explosion and impact problems, and also Abacus. Explicit. They are kind of similar. Okay, they are all used a lot in dynamic problems like explosion, impact problems. However, in this course, we will focus on static problems. And the finite element method is called the implicit method. Because for static problem, you cannot rely on time. Time is not a factor. You cannot march forward. You apply a load, everything settled, you just solve one time, right? So you have to invert a matrix to get everything satisfied. For that, we need to further derive that, okay? Because it is not appropriate to solve for explicit problems. As you can see here, if you use the explicit method, you start with a no state, you look at this, everything is known here. That's also known, only the stress is unknown. So you move this on the right, and then you estimate stress using this, okay? That's how the explicit method works. For implicit, even though this is known, we don't have a time, we don't have a small time to march forward. We have just like one step that we need to find the solution. So we cannot rely on this marching forward philosophy. We have to invert this thing to solve on that. Okay? Now, let's derive the implicit formula. We assume that the the material is linear elastic, okay? Now we assume an approximate solution. Assume a solution, which is this. The solution, this is a 3-component vector form, okay? You have U, V, W, okay? You can write it as U, V, W, component form. That can be written as N0 and then A0 plus N. Let me put this in a matrix form. Plus N this is U0. Hey, remember we said we are going to always write the approximate solution with consisting 2 terms. The first term is the term that will satisfy the essential boundary condition. Therefore, the second term, all the shape function will disappear on the essential boundary condition. Will be 0, okay? Therefore, and we use this as a weighting function, which is what we use here to derive that. At the very beginning, we use this delta U, it's just this times delta that, right? We don't need to include the essential boundary condition. That is why we can do that, because we have that term that will take care of the essential boundary condition. Right? So this satisfies essential boundary condition. This is 0 at SU. Okay. All right. Now with that, we can calculate the strain correspondingly. In terms of matrix notation, we will have one contribution from the essential boundary condition term here, and then another contribution. And this one, the derivative, we can denote it as B0 matrix, then U0. And this, then the derivative becomes B, and this is UA. Oh, UA. Okay, So this is the displacement, this is the strain. And then the stress is equal to the material matrix, stiffness matrix, times E here. Okay? This is the elastic material stiffness matrix, and we spent one lecture last time to talk about that. Okay? It consists of the Young's modulus, a Poisson ratio, etc. A 6x6 matrix. It is symmetric. Two submatrices on the upper right corner and the lower left corner are 0, and then the lower right corner is a diagonal matrix. The only full matrix is the upper left 3x3. So that's that guy. Okay. All right. With that, we can say epsilon is equal to that. So we have a D matrix times this. So B0 matrix times U0 plus a D matrix times this term B times UA, which is the nodal displacement. Okay? Once we have these three, we can substitute in here into this matrix. This equation is actually equation A-1, A-11. So I can say into A-11. In fact, we don't actually need this expression and that. We only need that, because these two do not appear explicitly here. So only that guy appears explicitly here. So now, when we put this in, we will have a B matrix transpose, and this sigma vector is equal to that. So we have a D material matrix, and then times B0, and then U0 plus a D matrix, and then B matrix, and then UA vector. This whole thing integrates with respect to volume, and then minus this thing, and transpose B dV over V minus ST, and then this one, NT T dx equals 0. Okay? Almost there. Well, we then rearrange. The idea when you solve the equation is that how to rearrange it. You will move all the terms that contain a null to the left side, all the terms that are null to the right side, right? So let's see at this point what terms are null, what terms are unknown. This one, the B matrix shape function, we propose it, so we know this is the derivative of that. It's also a null function. D, we assume material property is null. That's part of the shape function, so that's also null. This one, U0, is the prescribed displacement. So let's do that. Let's use a red pen. This is known. This is known. This is known. That is the prescribed displacement, which means it's null. So that's no. This guy, the nodal displacement, that's what we want to solve, right? So this is not null. And here, that's null. Boundary force must be given, otherwise it's unsolvable. traction is also given. Okay? You cannot ask me to solve a problem that you don't tell me what forces it is, right? Okay, we arrange, so we only keep this on the left side. All right, so we have B transpose times this D thing and this B matrix. All right, and also as far as integration is concerned, the nodal displacement is actually not a function of position. So you can take that out, okay? The integration is with respect to V and V, this whole thing, now I can take that out times UA vector. That's the only thing I will keep on the left. All others, I will move it to the right. Let me first write this one, which is N transpose B dVB. So that's that term. And then this term, the traction boundary condition as T, and this is N, and then T, and then T ds. So we have that term. And then we also have a third term, which is here, that consists of the contribution from essential boundary conditions. Okay? But because this is plus on the left, it becomes negative on the right. It's B transpose D V0 and then dV V, this whole thing times U0. Okay? So let me like that. This is the most important equation. Okay? And that's the formulation which is based on weak statement of elasticity, and it is almost ready for implementing. Okay? Now, the integration here, however, we in the shorthand just write it as integrate over the whole domain here again, and this is over the whole traction surface. When we implement in a finite element way, we are going to integrate it over each element, okay, and sum it all together. Therefore, we can further write it as once it's discretized into element, then the equation correspondingly will be written as this. All the integration will be over the element, but then in front you will have a summation sign. So V becomes V element. Element is from the first one up to the number of element. We can use small m, or we can just write it as UML, okay? We write it this way, n. And here will be B transpose D, and then B, and then dV. This whole thing times UA equals, and then here again we need to integrate over each element, and T body force dV summation E from 1 to n, then plus this one is also over as element traction N matrix transpose T traction and then ds. And then we need to sum from 1 to last element, okay, like that. And this one is the same, minus B transpose D and then B 0 dV over V element. V element. This whole thing must sum from from 1 to n. And then we have U0 here. Okay, these two equations are exactly the same. This is taking the whole model view. This is taking the element view, okay? You look at what is inside, you do things at the element level, but don't forget to put everything together because the whole model consists n number of elements. Here, n is equal to the total number of element. And that's it. Okay? And this equation now is truly ready for implementation. And this is the equation A-18. In fact, our finite element method, when you program it, you use this. And if you look a little bit more carefully, this term here give you a matrix. If it is symmetric at the element level, this is actually called this element stiffness matrix. This one will give you the body force vector. This gives you the traction force vector. This gives you the essential boundary contribution vector. Okay, but there's a negative sign here. That's the only difference. This is positive. This is negative. Okay. The reason it's negative is that it was original on the left side, which is positive. But because it's null, we move to the right and becomes negative. I think that will be it. This is a short chapter. Now we are getting ready to move on to almost the next phase. We can program it, okay? After a few lectures, and then we will roll up the sleeve and start programming. All right, thank you. That's for today.